Okay. Hello, everyone. This is our group, and our topic is deep dynamic compaction. I'm Ipe.
I'm Richard.
I'm Zach.
I'm Chris.
Libby.
Brennan.
Danielle.
First of all, I will talk about the background about the DDC, and here is some list of the history how it developed. During the 1930s, the pre-modern DDC was emerging from field study in Germany and the United States, and then the DDC as a compaction method in 1969, and at the same time, the Louis Maynard developed the technique into its present state as a method of deep densification. Also, the DDC has been called by other names including heavy tamping, dynamic consolidation, and pounding. And then in 1986, Lucas defined DDC as a densification of soil deposits by means of repeatedly dropping a heavy weight onto the ground surface. And then at 2006, the DDC induced compaction for partly saturated soil is governed by the explosion of air voids within the soil mass. Like you can see here, like the DDC developed all the time. So, and next.
Just right here.
Thanks for the history part, and but we have to know what is DDC, and DDC is a deep dynamic compaction. And what is a deep dynamic compaction? Can you go back?
Yeah.
This is a method which is used to increase the density of the soil and fill loose soil deposits. And the basic principle is to send high energy waves through a compressible soil layer in order to improve the depth of its geotechnical purpose. And the process is very simple. You just drop a heavy steel or concrete, maybe about 5 to 25 tons, and then down to the ground, and the height may be about 80 to 100 meters, and this kind of steel may be about maybe circular, and it's about the diameter is 4 to 12, and that is how it works. And basically speaking, DDC is a method to improve the ground level, the ground abilities, and yeah.
Go left to right? I don't know. I think it goes the other way.
How did you go to the next? Oh. Okay. What's the advantage for the DDC? So you see, it's an economical method of improving engineering properties, and also it can aid in making use of land that may not be economically viable using traditional construction. And also it will increase bearing capacity, decrease settlement, and liquefaction potential for plant and structures. And during my research, I found the cost of the deep dynamic compaction. It all depends on the land, depends on the size of the land, depends on the geographic location. But the average range for each square foot is $1.5 to $2.75. And in order to make the deep compaction more clearly, we have to watch a video.
Just We'll go by.
Yeah.
We won't need to watch
Okay, we have
So
already
video.
finished the video.
Yeah.
So, the method of dynamic compaction affects 3 soil characteristics: compressibility, liquefaction potential, and permeability. On Monday, we learned that a high total pressure was needed to keep structures stable. A reduction of voids increases the density and therefore increasing buried capacity and a factor of safety. Liquefaction occurs when effective stress of a soil goes to 0, giving the soil the property of a liquid. I forgot what's wrong with this. Oh my god. Alright, try that again. Liquefaction occurs when the effective stress of a soil goes to 0, giving the soil the property of a liquid. This reduces the shear capacity to 0. By lowering the void ratio, effective stress increases, which increases the factor of safety. What's wrong with this? It's got a minute to him.
Maybe you should click this.
Yeah.
Yeah.
Alright.
I'm just
Lowering the permeability of a soil decreases the potential for quick condition and piping by increasing the critical hydraulic gradient of the soil. We're going to try this one more time tomorrow. It's bad.
Alright, so our first case study that we did was the Cole Harbour Marina. The Cole Harbour Marina is located in Vancouver, British Columbia. And what the case study was about, well, what they did in this event is they were reinforcing a dike in a marina. They were reinforcing it because it's along a fault line, so it's subject to vibration from earthquakes. So they're doing to prevent liquefaction and lateral spreading of the soil, which could undermine buildings that are close by. So the design of the dike that they created was they had a compaction zone that was 1.5 to 21.5 meters wide. It varied depending on what the soil was right there. And they were compressing, the column of soil that they added was 13 meters deep, and they were compressing it down to 10 meters. And the material that used for the import sand and gravel in this was under 75 millimeters, which is around 3 feet, or 3 inches, not 3 feet. So the weight that they used for this was a 20-ton circular weight that they were dropping from a height of 25 meters. They were dropping it from a lower height because it was an urban area, so they didn't want to vibrate buildings close by too badly. Which was good. It was a good idea, but in one spot it didn't work because there was a hotel that was too close by. When they were dropping the weight, it created vibrations of about 12.5 millimeters per second, up to a distance of 40 meters. So buildings couldn't be closer than 40 meters. So what they had to do when there was a hotel closer than that distance was they had to use vibrocompaction, which is basically just driving a shaft down into the soil and vibrating it to compact it. And for quality assurance in this case, they used a standard penetration test in the field to make sure they were compacting it to the right degree. And after the construction was done, they hired an outside company to do a Becker test of it just to make sure it was right.
Okay, so the next case study is the DART bus facility in Dallas, Texas. And they were trying to build a new maintenance facility, but the problem was that it was on a 20-acre abandoned sand pit that was filled with clay soils and construction rubble, and then underlain with limestone rock. So the solution that they came up with was dynamic compaction to densify the fill and provide long-term acceptable sediments for the foundation. So for the dynamic compaction, they used two 200-ton cranes to speed up the process with an 18-ton weight with drops from up to 80 feet. And they were at predetermined locations, varying from spacings of 10 to 20 feet to match the energy levels of the thickness of the fill that needed to be treated. So in the end, they built the facility and they used penetration tests to show that the fill density requirements were met, and that they monitored the existing structures for vibrations to make sure that those weren't affected. And the overall site elevation dropped about 2 feet, so that reduced the void ratio of the fill.
So our last case study was the building of Riverview Apartments, which is in Salt Lake City, Utah, which is considered to be a seismic active region, which was the main problem because the site was located, it had 2 faults located just 3 miles within the region of where they wanted to build. They conducted tests to find out that there was a 10% chance of earthquake, which would have a max ground acceleration of 0.3 Gs, which, like, in terms of real life, if you've ever been on the Tower of Doom, you would, like, experience 3 Gs on the way down, so that's like 1/10 of that. Due to really loose soil, it was necessary for them to use the compaction because they needed to place shallow footings. But each drop creates a lateral. I can't think of the word I'm looking for.
It's okay.
No, it creates waves laterally, which would impact the surrounding attractions, which consisted of a restaurant, an office, and a sewer pipeline, which was the main concern. So they had to excavate the pipeline to make sure that it wasn't being affected because it came into 25 feet of the site. So after testing it, they realized that because of the rigidness of the pipeline, damping occurred, and it actually only had 1/2 of the waves that was being occurred in the soils next to the pipeline. So in order to continue the compaction, all they had to do was lower the dropping height of the compaction, and then the other structures were in acceptable tolerance of 0.5 inches per second, so they could go ahead and keep doing regular compaction for the rest of the site. And at the end, they used a cone penetrometer test, which is like what we did in lab, and they realized that they densified to the specific criteria equivalent of the 25 of the standard Proctor test.
This is the picture, so.
Oh.
Why not?
This leads us to the summary of our presentation. So now we know that deep dynamic compaction is a relatively new technique. It's around the last 35 years. It's also cost-effective soil treatment technique that has a wide range of applications and advantages. As Richard stated before, it could cost as much as $1.50 to $2.75 per square foot. This depends also on the site and the geographic location of the project. Looking at other soil treatment techniques such as lime stabilization, which can cost as much as $4 per square yard or $35 per square feet. This is relatively cheap. It's also, as we stated, the repeated impact of weights, which create high energy waves, generally applied in different phases following a preset grid. This is typically a square grid with spacing between each drop, which is determined by the subsurface conditions of the soil. It helps to mitigate soil liquefaction while increasing the bearing capacity compressibility and permeability of soils, and it can also be used to prevent sinkholes by collapsing voids prior to construction. It's also a versatile technique and has barely any limitations on the type of soil or projects that it can be used for. There's cases in which it's been successfully used on rocks, coral layers, sand, and non-saturated silt and clay soils. The suggestions that we've come up with are, to make sure that this is the right technique for the project that you're doing. If you're in this picture, there's a construction site with a lot of cities around it. It's in a congested city. The dynamic energy applied to the soil could actually have an effect on nearby structures. And our suggestion is to sort of use a combination of compaction techniques, such as using deep dynamic compaction and vibrocompaction, which only affects structures within a 3-meter radius of where you're doing it. And also, as we've discussed in some of our other case studies, just have proper site assessment and make sure that you have well-qualified engineers to make the decisions that you need. And this leads us to questions. Questions.